given the questions to the right. So getting started, we can define independent events using conditional probabilities. Remember back from standard 12, we define independent events like this. Two events are called independent if the occurrence of one event has no impact on the chance that another also occurs. It has no impact on the probability of another event also happening. What's a good example of independent events? A pair of events that are independent. How about flipping a coin? I flip a coin once, I get tails. Does that affect the chance of getting tails again on the next time I flip the coin? No, it's still 50-50, right? The outcome of the first toss has no impact on the outcome of the second, right? How about dependent events? Go back to those cards from yesterday. When I drew the card, did I put it back? No. So the next draw is impacted by whatever I took out on the first draw. That's not independent anymore. We can test to see if two events are independent using conditional probabilities. So this statement right here says that two events, A and B, are independent if the following statement is true. The probability of A is the same as the probability of A given that B is also happening. This is just the probability of A. A and B are independent if the probability of A is the same as the probability of A given B. What does that given B mean? What has already happened when I say probability of A given B?
B is happening.
B is already happening. But isn't this probability still the same as the probability of A by itself? Does B have any impact on the probability of A if these two probabilities are true? No. Whether B occurred on this conditional probability or B hasn't occurred, they're still the same, right? So the likelihood of A happening is not affected by whether B happened or not if these are two independent events. The probability of B already having happened, has no impact on whether A occurs or not. That makes them independent of each other. Whether B happens or not has no impact on the probability of A. Okay. We'll come to that here in just a second as I work through some of these conditional probabilities on this question. So let's try this. For Thanksgiving, 75% of people eat turkey, 40% of people eat ham, and 25% eat both. Let's use that.
We're ready when you're ready.
Yeah, go ahead, guys. If you need some lunch. No. So let's use these defined probabilities to draw a Venn diagram. I've got two events, ham and turkey. Are they mutually exclusive or are they overlapping? Can you do both? So overlapping. Are mutually exclusive? They are overlapping. So let's draw a Venn diagram with two intersecting circles. "75% of people eat turkey, 40% eat ham." So that means that the entirety of the turkey set, the turkey circle, has to add up to 75%. What goes here and here, those that have both and those that have just turkey and not ham have to have a sum total of 75%. 40% eat ham, so the entirety of the ham set, the ham circle, has to add up to 40%. I also know 25% eat both, so that can only go in one place. Let's put the 25%. in the overlap. So what percent eat just turkey? 50. These two things have to add up to 75, but I've already got 25 in the overlap. That leaves 50% for those that eat turkey only. What percent eat just ham? Well, I need another 15 for the other part to make 40 total. What percent have neither? It's just the other part that makes the 100% in total. 15 and 25 is 40, plus 50 makes 90, so 10% has neither turkey nor ham.
Why would you have neither? What else would you eat?
Anything else you want? I have some people who just eat pasta for Thanksgiving. Some families I know probably just have a big bowl of spaghetti.
It really just depends who's cooking.
Exactly. All right. So let's look at some of these probabilities using the Venn diagram we've got laid out for our two overlapping events. Read this carefully. What are we already given for our condition? What are we assuming is true? If you eat turkey, what's the chance that you also have ham? What are we starting with? What do we know to get started? We have to have eaten turkey. So setting up my notation, we have to eat turkey first. I'm going to put that after the vertical bar. I have to have eaten turkey first. If you've eaten turkey, what's the chance that you've also had ham? This would be equal to, of all the people that eat turkey, out of that proportion, what also have ham, turkey and ham. Let's build this from the ground up. In the Venn diagram, I have to know that you eat turkey. So I have to live inside the turkey set. What's the total proportion of people that eat turkey? As I'm covering up the other numbers that eat ham or nothing. 75. So I'm restricting myself to only this 75% because I have to know that you eat turkey to start with. I have to know that this is true. And of those that eat turkey, what percent also have ham for the top part of the proportion? Because those eat both, right? Ham and turkey. 25 out of 75, which is 1/3, or 33.3%. Reading the question, setting up your probability, and reading the Venn diagram to find the answer out of the parts there. We got it so far? Okay, I'm going to change it around a little bit. On number 2, you have turkey, given that you eat ham. So how is this different?
You eat ham.
I eat ham to start, right? I'm changing the condition. Given that you eat ham, what's the likelihood of you also eating turkey on Thanksgiving? So this would be defined as, of the proportion that eats ham, what part also eats turkey? So given that we have to eat ham to start with, I have to live inside the ham circle. I can't have just turkey and I can't have neither. So what proportion has ham?
40%.
And of that 40%, still covering up everything that's outside the ham circle, of that 40%, what part also eats turkey? The 25 that eats both, right? 25 out of 40, that would be 5/8, or 0.625, 62.5%. Okay, let's try some tougher ones. Number 3, for example. Given that you have turkey, what's the probability that you do not eat ham? Okay, start with the assumption. We know you eat turkey. Given this condition of having turkey, what am I also trying to find the probability of? So I'm going to go ham prime, H prime. This is the opposite of having ham, not having ham. So, what part of my table or my Venn diagram has turkey? I'm going to cover up those that have ham and neither. It's the same 75% we started with. And of those that eat turkey, what part does not have ham? Or in other words, what part just eats turkey? 50. These people eat turkey but do not eat ham. So of the 75 that eat turkey, these people do not have ham. Does that make sense? It's just the 50% here that only have turkey. So 50 out of 75, that would be 2/3 or 0.6667. Okay, let's try the next two. Just 4 and 5, please. I'll give you a couple minutes to work through those on your own before we answer if having ham and turkey are independent events using conditional probabilities. Number 4, if you do not eat ham, what's the probability that you eat turkey? Number 5, you do not eat ham. What's that probability if you do not have turkey? Table set up, use that table to find your probability. Check those, they should be good. Sometimes you get kind of wordy, so you really have to think about what you're starting with first. Doing knots, working around. What's the probability that you do not eat ham? Given that you do not eat ham, what's the probability that you have turkey? So what are we starting with? What do I know to be true to begin with? You're not eating ham. If you don't have ham, what's the chance that you have turkey? So not eating ham is what percent? These people here, outside the ham circle. Cover up everything inside the ham set. That leaves the other 60%. Of those that don't eat ham, of that 60%, what part has turkey? So not eating ham, if I cover that up, what part has turkey? Well, which number is inside the turkey circle? 50%. So 50 out of 60, which becomes the 5/6 or 83.3 repeating percent there to the right in green. And number 5, this would be the double knots. So what's the probability that you do not eat ham if you do not have turkey? So we've got our assumption of not having turkey. Of that part, what's the chance that you also do not eat ham? So not having turkey would be what percent? Not having turkey. Because it's everything outside the turkey set. The 15% that just have ham and the 10% that have neither. Of that 25%, what part does not have turkey? Or not eat ham, pardon me. Of that 25%, what part does not eat ham again? 10. 10 out of 25, or just 2/5, 40%. All right, so work with conditional probabilities in Venn diagrams. Overlapping sets, finding conditional probability. Let's see if having ham and turkey are independent on line number 6. Are eating turkey and ham for Thanksgiving independent? If they're independent, that means that eating turkey has no impact on the chance that you also have ham and vice versa. So let's look up those probabilities. What's the probability that you have turkey compared with the probability that if you have ham, what's the chance you have turkey? Let's see if ham changes the probability that you also have turkey when I compare these two together. What's the probability that you have turkey? That was given to us originally. 25%. Now, turkey given ham, given that you have ham, turkey given ham, isn't that the 62.5% right here?
They're not the same.
So what does that mean?
They are not independent.
Okay, they're not independent. So what does having ham do to the likelihood of you also having turkey? What does having ham do to the likelihood of having turkey? Because it's lower than 75%, right? If you have ham, you're more likely to not have turkey. So they're not independent. Having ham changes the likelihood of you having turkey. And I can compare these two probabilities to find that out. You could also do the same thing using ham as the comparison. Let's look up these probabilities. Compare the chance that you have ham with the chance that if you have turkey, you also have ham. Let's see what turkey does to the likelihood of you having ham. The probability of having ham was 40%.
0.3%.
Now we did ham given turkey earlier. That was over here, 33.3%. If they're independent, turkey would have no impact on you having ham. Therefore, these would be the same. Is that the case anymore? No. What does having turkey do to the likelihood of you having ham? It's lower. These are not independent. For example, having ham lowers the chance that you have turkey. Lowers chance of having turkey. All right, I got that. We did some Venn diagrams. I have one more thing to look at with this contingency table here on the back wall. Let's practice this and we'll get some stuff going on Schoology for you guys to try on your own. All right, so here's the setup. Mr. Hansen is always grouchy when it rains. His students decided to chart every time it rains and every time he was grouchy. And we can see that data in the bottom row and right-handed column. How many days were charted in total? What's the total number of days we got data for? 25. That's the grand total here in the bottom right corner, right? We did this for like, what, 5 weeks of school or something, perhaps. So 25 days in total. How many days did it rain?
5.
Rained 5 days, didn't rain 20 days. How many days was I grouchy for? 10 grouchy days, 15 non-grouchy days, okay? How many days was I grouchy and raining?
5.
How many days was I grouchy and raining? No, that's just rainy days. It could be rainy with me being grouchy or not grouchy. I don't know how many days I was grouchy and raining on. That's what I got to fill out. Okay? So we take the chart, we chart every time it rains, every time I was grouchy. They discovered that Mr. Hansen's mood and rainy days are independent. They discovered that my mood and the weather are independent of each other. The weather has no impact on the probability that I'm in a bad mood or not. I'm in a grouchy mood. So let's fill out the contingency table, assuming that these are 2 independent events. If these are independent events, that means that the probability that it rained and the probability that it rained given that I was grouchy are the same thing, right? If these are independent events, my mood has no impact on the chance that it's also raining, right? I know there's probability already. What's the probability it rained for these 25 days?
20%.
Because it's what divided by what, Jade? 5 over 25. 25 days in total, it rained for 5 of them. Okay, now let's look at the next probability. Let's set this up. What's the proportion of, if I'm grouchy, it's also raining? If I'm grouchy means you have to live in this left-handed column. I have to assume that you're grouchy or that I'm grouchy. So I'm looking in this column. How many days was I grouchy? 10. How many days was it also raining when I was grouchy? I don't know that. That's this empty cell up here in the top corner. Of the 10 days where I was grouchy, how many of them was it raining? That's what we're trying to figure out. Once again, what do I know about those 2 probabilities? Because it's independent. So let's just make proportion. 5 out of 25 has to be equal to x over 10. 5 over 25 is proportional to this empty cell divided by 10. Just compare the 4 corners. X over 10 was 5 over 25 because these are 2 independent events anyway. It should be equal. Well, find cross products. 25x equals 50. What times 25 makes 50? 2. You said 20%. Isn't 20% of 10 2? Same thing. Okay, now I should be able to fill in the rest. It rained for 5 days. I was grouchy for 2 of them. How many rainy days was I not grouchy on? I was grouchy for 10 days. It rained for 2 of them. How many days did it not rain when I was grouchy? The other 8. It should be 12. Assuming that these are independent, makes everything in here kind of proportional, equal to each other. The probability that it rained, 5 out of 25, should be the same as the conditional probability where if I'm grouchy, it also rains. So I can find this empty cell by setting up proportionality. We'll practice some more of that tomorrow.